When does it make sense to use a failover cluster instance in Linux? Let's talk about that. Welcome to this video on SQL Server on Linux. My name is Kevin Fiesel, and I'm the proprietor of Catalxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. So far in this series, I've walked you through several scenarios around SQL Server for Linux, showing you how to perform actions on Ubuntu 22.04 and sometimes Ubuntu 20.04. This video will be a little different as it requires some remote storage that I don't really have, and there also aren't direct instructions on how to do this in Ubuntu, though all of the tools are available for some level of operation. As a result, we're going to spend the entire video in the classroom talking primarily about Red Hat Enterprise Linux, so grab a seat and make yourself comfortable. Our topic today is failover cluster instances in SQL Server on Linux. We are going to hit on a few key points. First, what is a failover cluster instance and why should anybody care? Second, how do I create a failover cluster instance? Third, how do I perform a failover? Let's take each of these questions one at a time. The first question is, what is a failover cluster instance? A lot of this is in the name itself. We have an instance, that is a single entity. That instance is a cluster of machines, so more than one server should be part of that instance. And its purpose is to handle failover events, such as one of the servers spontaneously combusting, letting you fail over to another server to handle incoming traffic. Failover cluster instances are part of a business continuity solution for SQL Server. Business continuity is a concept made up of two critical parts, high availability and disaster recovery, and failover cluster instances fit neatly into the former. Here's an image covering the basic idea at a really high level. We have three servers that are all part of a failover cluster instance. These servers have their own compute and RAM, as well as network interface cards, or NICs. These machines may be physical servers or virtual machines, though if you do want to host everything on virtual machines, it would be wise to make sure you don't have all of the VMs on the same physical hardware. The reason is that failover cluster instances are intended to provide some level of hardware redundancy, and I'll build a stylized example to show you why. Let's suppose we have a user connecting to our SQL Server instance and accessing data from one or more databases. This instance is part of a failover cluster containing the three physical servers. Those physical servers have their independent hardware, including independent NICs. They also have connections to shared storage, typically a storage area network or a SAN. The SAN itself contains a number of disks hosting our data. We implement disk redundancy here using a technique known as RAID, or Redundant Array of Independent Disks. If you want to learn more about RAID, I'll leave a link to a primer in the description below. But for the sake of simplicity, depending on the specific options we choose, RAID gives us the peace of mind that if one or possibly more drives fail, we won't lose our data. In this case, suppose we have 2 of our 7 drives fail, and depending on the RAID level, we may still be able to chug along like nothing ever happened, at least until we can swap in new drives. So that's the disk side of the house. The failover cluster uses shared disk so that each server does not have its own independent copy of your data. On the compute side of the house, we have one primary node in the failover cluster instance and one or more secondary nodes. The primary node is responsible for answering any user requests, so a user who connects on port 1433 over TCP with the intent of submitting a T-SQL query will actually talk to the primary node, and that primary node will read data off of the SAN to respond to the user request. Anything stored in memory, such as pages in the buffer pool, those are on the primary node itself, but not any of the secondaries. In other words, this is not a scale-out scenario for SQL Server. Only one of these 3 servers can accept user requests, and the other 2 cannot, even if we tried to connect directly to that physical machine. This is because all three of the machines are working from the same shared storage, and we would not want to run into a situation in which one user updates a table through physical server 1, another user updates the same table through physical server 2, and the two updates are incompatible. We live in a relational database world where the quality of data actually matters, and that kind of operation is a no-go. So what is the point of this added complexity if it's not to make our queries go faster or to scale out user requests? Well, the answer is it saves our bacon if one of these servers fails for whatever reason. Let's say that our primary node is chugging along, answering user requests like a boss, when all of a sudden it explodes. It turns out that our corporate rivals packed Simtex around our RAM, detonating it at the most inopportune time for us. Our CEO is just about to hit the stage and talk about this quarter's major achievements, and we need to get those results out there or else the stock price will tank. While our street samurai are planning a counteroffensive, we've got a job to do. There's no way we can rebuild a server in time, but the failover cluster lets us promote one of the existing secondaries to be the primary. Now that server picks back up where the other one left off. If there were any uncommitted transactions running when the old primary bit the dust, yeah, we will have lost those. But anything committed is sure to be there. Okay, suppose you don't live in a Shadowrun universe and you typically don't have to worry about explosive sabotage. There are still good reasons to use failover cluster instances. First, machines do fail, and sometimes they do light on fire. Second, a much more prosaic and less inflammatory explanation is that we need to keep these servers patched. Those patch events may require a reboot, or at least would make the server unresponsive during patching. What we can do in this scenario is to patch the secondaries first. Those secondaries are sitting around and not serving users, so we can patch them whenever we'd like, rebooting them if we need to. Then, when it comes time to patch the primary, we perform a failover. While the old primary is getting patches applied, our new primary is serving traffic. And if we do it right, there's little to no disruption for end users. They keep sending queries and keep getting responses with maybe a one-time blip of a few seconds along the way. Eventually, our old primary is up to date with patches, and it can serve as an available secondary until the next time we need to fail things over. Something important to consider here is that there is no preferred primary in a failover cluster instance. Any one of these servers can serve as the primary for as long as we'd like, and the rest are secondaries. This means that, in an ideal world, our servers have exactly the same configuration in terms of hardware. Same CPU, same RAM, same NIC brand, same model, same everything. They should be entirely interchangeable. I am also, by the way, ignoring anything about licensing in this. Just talk to a licensing expert. I'm not one of them. There may be licensing reasons why you have to have a single instance as a primary, but I don't want to go down that road because I will very quickly say something that's wrong. So let's just assume all of these are licensed, all of these are fully set up. Now, in many cases, though, you may need to cheap out and have one fully stacked primary and a less powerful secondary. That's not a great solution, but if you simply don't have the budget available for a proper secondary, it may be what you're stuck with. In that case, you would likely have two failover events for patching. Once to take your main server down and begin patching, and once when this main server is patched and ready to take back over as the primary. That's a little less convenient for your users, but it's not catastrophic. The problem comes into play if the beefy main server goes out of commission for several days and you have to rely on the stringy alternate server. So my recommendation is match hardware whenever possible for each of those servers. It's not a strict requirement, but failing to do so can hurt you further down the line. Okay, that's question one resolved. What a failover cluster instance is, and even why we should care about it. Which, by the way, is two questions, so there was a bonus answer thrown in there for free. Now let's talk about question two. How do we create a failover cluster instance, specifically for SQL Server on Linux? That's where, normally, we would be headed out of the classroom and into a demo. Unfortunately, it's kind of a no-go today because it requires officially either Red Hat Enterprise Linux or SUSE Linux Enterprise Server. Both of those are paid products and, well, I have not yet sold out for that sweet, sweet YouTube cash. That said, both of these solutions are built on Pacemaker, an open source high availability cluster stack. Pacemaker itself supports Ubuntu, and we're even going to use it in the next video, so stay tuned for that. Also, I think the only thing missing in Ubuntu is the ability to perform automated failover, as all of the Failover Cluster Instance components are available in the Ubuntu 2204 repo. So if you are okay with a Failover Cluster Instance with only manual failover, I think that's possible to achieve. In the meantime, however, let's talk a little bit about this image. We've already seen my depiction of a Failover Cluster Instance. In this image, that prior picture represents the hardware layer, Linux servers, and shared storage. On top of that is a pair of software solutions, CoroSync and Pacemaker. CoroSync, or specifically CoroSync 2, is a cluster engine and acts as the messaging system that keeps track of whether processes are available. Pacemaker is the cluster resource manager that sits on top of CoroSync and serves as the brains of the operation, reacting to events that occur like nodes joining or leaving the cluster, or handling failover due to resource failure, or even a scheduled maintenance task. One of the key things that Pacemaker does is called fencing, which makes one or more nodes in a cluster unable to run resources. This is important for preventing a split brain scenario, where you have multiple nodes believing that each one of them is the primary and accepting user traffic. This is a scenario that I talked about earlier when I mentioned that SQL Server Failover Cluster Instances are not a scale-out technology. Neither is Pacemaker. At the top of this, we have SQL Server services running on the different Linux servers. In this case, one of the two is highlighted and the other is not. This tells us only that one server is active at a given time and the other is sitting back in wait, in case it becomes necessary later. Then, in the notes, we can see that there are some differences between Failover Cluster Instances in Windows using Windows Server Failover Clustering versus on Linux with Pacemaker and CoroSync. There is not as tight an integration between SQL Server and Pacemaker, which makes sense. WSFC comes from the same company as SQL Server, so you would hope that teams would work more closely to make sure the products integrate well compared to some open source technology that supports a variety of products. After that, the documentation covers a pair of relevant notes. The first is that you are capped at a maximum of 16 nodes in your Failover Cluster instance due to Pacemaker limitations. But that's on Enterprise Edition. If you're on Standard Edition, you are capped at 2 nodes, as that's a licensing restriction. When it comes to IP addresses, each server needs its own unique IP address, and so does the Failover Cluster instance. You'll also need to do the DNS setup so users contact the Failover Cluster instance rather than any individual server. This is something we normally get for free with WSFC, but is a little bit of extra work on the Linux side. Now we get to the next big thing, shared storage. SQL Server supports 3 options for shared storage: iSCSI, Network File System, and Server Message Block. You'll already be using one of the 3 in your corporate environment, so go with that one. My understanding is that SMB is the slowest option of the 3, but in fairness, I have never been a storage admin, so ask the people who know what they're doing for that. I know how to overwhelm storage subsystems, not how to maintain them. At a high level, the instructions are the same regardless of the shared storage technology. First, you configure the shared storage. Then, you mount that shared storage on each of the nodes. As a note, they point out that you will need system databases on shared storage, and that does include TempDB. With Windows Server Failover Clustering, you could have TempDB run on local storage, like a direct attached NVMe drive. No can do on Linux though. Everything's got to be on that shared storage. Now let's talk about how to do this in Red Hat Enterprise Linux. The first thing to do is make sure you have RHEL with the high availability add-on installed. As a quick note, that is a commercial add-on. The next step is to install SQL Server on Linux on all of your nodes, including your primary and any secondary nodes. For each secondary node, disable the SQL Server service so that it does not try to run. There's a quick note in here about taking the machine key from your primary node and copying it over to all of your secondaries, so make sure you do that. On your primary node, create a new SQL authenticated login for Pacemaker to use. At a minimum, it needs view server state, setup admin, and alter any linked server. And I would do that rather than granting sysadmin like the code example does. I instinctively dislike granting sysadmin to service accounts. Anyhow, after you've granted view server state, set up admin, and alter any linked server, stop and disable SQL Server on the primary. The next thing you should do is configure etc/hosts on each VM, ensuring that each host includes the IP address and name of each cluster node. And make sure those host names are 15 characters or fewer. We saw in the Polybase video one of the negative outcomes you can run into if you fail to follow that instruction. Now it's time to configure the Failover Cluster Instances storage. I'm going to leave links in the description below for each of the three options, one for iSCSI, one for NFS, one for SMB. The instructions are quite different for each technology, so figure out which one you need and follow those instructions. Once you've done that, you'll need to install Pacemaker. There is a little bit of prep work to do up front around storing the username and password for your Pacemaker account. And this, by the way, is a really good reason not to give that account sysadmin privileges. I don't like the idea of a plain text file having usernames and passwords sitting around, even if we will limit who gets access to that file. The next several instructions are pretty straightforward. We start by installing software. Then we change the password for the HA cluster account that Pacemaker and CoroSync use. After that, we enable and start the PCSD and Pacemaker services. PCSD is the Pacemaker and CoroSync Configuration System daemon. Finally, we install the MS SQL Server Failover Cluster Instance service on each node, which is MS-SQL-Server-HA. The last bit is to configure the Failover Cluster Instance. There are a couple of steps here, and they depend on which type of network storage you are using. But for each one, you'll use the Pacemaker Configuration Service to create a disk resource and associate it with your cluster. Then there's the rest of the story. The final instructions wrap up the installation process. First, we will need to provide Pacemaker with the IP address that the Failover Cluster Instance will use. Then, we create the FCI resource itself. Once that's done, we bring the resources online and make sure we can connect to SQL Server using the DNS name of the Failover Cluster Instance. If that works, you can check that you're connected to the primary node. Then, fail over to the secondary, run the tests again to make sure that the other service is still up and that you're still getting the Failover Cluster Instance name in @server name and the secondary host's name from the computer name physical net BIOS server property. So that's the process of configuring a failover cluster instance. Now we move on to the third question. How do failover operations occur? Well, if you're using Red Hat Enterprise Linux or SUSE Linux Enterprise Server, you can use the high availability agent to perform automated failover. There's a note for people coming from Windows Server failover cluster land that the expected behavior is a little different. First, you can't say to failover from server 1 to server 2, followed by server 3 as a preference list. Instead, Pacemaker picks the server that takes over. Now, this isn't too bad if all of your servers have equivalent hardware, but it is something to keep in mind. The other option is manual failover. And this is where we tie things back and say that, yeah, you can do most of this with Ubuntu if you have the appropriate network storage device. You can definitely perform manual failover, though I don't think you can get the automated failover capabilities that RHEL and SLES provide, so that does somewhat hamper the value here. But if you do want to perform a manual failover, you run the resource move operation, telling which cluster node you'd like to use. And in fairness, I've worked at places where manual failover was preferable because those places want a human in the loop to make sure the failover was reasonable. Granted, that was often because the secondary server wasn't as powerful as the primary or because the network was kind of flaky and otherwise you'd be bouncing back and forth a lot. But the point I'm driving home is that there can be reasons why no automated failover is okay. That's going to do it for us today. I know that life's better when there's a demo of me futzing about on the command line, but I do promise we'll get back to that in the next episode. We'll have links and show notes in the description below, and until we see each other in the next video, take care.